Hello everyone, this is video 4.6 and we're going to be looking at the standard multiplication algorithm. So for most of you, this is going to be the way that you probably learned it. And so we're going to be connecting the models that we've seen up to this point to the actual algorithm. So let's get started. So as a little reminder, um, the algorithm needs to be supported by some sort of concrete model. So we don't want students just doing an algorithm and they have no idea why it works. Um, that's not the kind of math that we want to be teaching. So we want students to be able to do the algorithm and be able to visualize or understand or comprehend or whatever why this algorithm works the way that it works. And then that way, if the student is misapplying the algorithm, they're doing something incorrect with the algorithm, you can say, oh no, let's go back and look at the concrete model. Let's go back and look at this rectangle or look at, whatever, and see why this doesn't work. It'll help you sort of like solve issues around the algorithm. At the same time, we don't want students doing 3 or 4 digit multiplication by drawing a bunch of rectangles. So these concrete models need to be extended into efficient, quick, effective algorithms. So the abstraction and the concrete are going to work together. Um, one's going to support the other, one's going to be an extension of the other, but they all need to work together harmoniously. We don't want to be all algorithm. We don't want to be all concrete. We want to be a nice balance of the two. So let's start at the beginning. 1 digit times 1 digit. This is a little bit of a refresher because we've looked at this already a while ago. If we take a problem like 3 times 4, then if we go back to the very beginning of multiplication, we know we can write this as a little rectangle, a 3 by 4 or a 4 by 3, depending on how you want to look at it, rectangle. And so this shows our commutativity. This allows us to get to this number 12, our product. Eventually, though, we want these things to become facts. I mean, we want these to become memorized. I know it's kind of a dirty word around math instruction, or really around sort of teaching in general. But again, we want this to be an abstraction. This concrete model, drawing this rectangle every single time isn't going to cut it. So again, we want students to memorize their facts, but we also want the facts to be supported by some sort of model, a nice harmonious balance of the two. But it's all going to start with this 1 digit times 1 digit multiplication. Okay, so 3 times 14, we can start off by using our area model that we saw previously. And so our 3 times 14, well, we can break this into 10 and 4. And so now we've got this is 30 and this is 12. And so we've got our product of 42. Nice and concrete, looking at rectangles. We're doing the distributive property without maybe calling it the distributive property. We're just looking at sort of basic ideas around multiplication. Now this will abstract into the actual distributive property. And so now we're moving away from this concrete picture, we're moving away from that model, and we're getting into something that's purely symbolic. But again, this distributive property is supported by this rectangle. So the reasoning should be clear how this is working and why this is working. Now this will then be abstracted a little bit further into this vertical form of the distributive property. So I'm going to write the same thing, but I'm just going to write it vertically like this, and it still solves the same. This is still 3 times 4 is 12, and then 10 times 3 makes 30, and I get 42. The reason for moving it vertically is so that we can eventually get to this actual algorithm. And so once we get to this form, we're in its sort of most abstracted sense here. So 4 times 3 makes 12. And now, if we've done the work up to this, you can tell because this making 30 won't be confusing. If you have students that are doing 1 times 3 is 3 and add this magic 0, that's a big clue that students have no clue why this algorithm works, right? But if they can understand that this 1 is really this 10, and then 10 times 3 makes 30, and that this is not 1 times 3 makes 3 with a magic 0, this is what we want. We want them to understand how place value, expanded form, distributive property, all these things come together to make this efficient algorithm, and we can get this 42 in a quick way. Drawing these pictures every single time, again, not really necessary. It's not efficient. It's not the way to solve these problems after a certain point. But this needs to be supported by this. So this model needs to evolve into the algorithm. This algorithm needs to be supported by that diagram. So you see how they work together. And in between, we have these things here called intermediate algorithms, which are different blends and combinations of concrete and abstract. And so as students start at the beginning and then start to move toward this abstraction, we may need to take more or fewer steps along the way, depending on how well they understand the abstraction along the way. So knowing a lot of these intermediate algorithms helps you be able to figure out where students are, where they need to be, where they can be, and so on and so on and so on. So now we can look at a problem in 2-digit addition. So like 46 times 27. And so this area model from the beginning, we looked at in the previous video, 46 by 27. And so we can start off by splitting this up into 10, 10, and 7, and then 46, so 10, 10, 10, 10, and 6. And so now we can count this up and see what we get. So this is 1, 2, 3, 4, 5, 6, 7, 800. This is 60 and 60. So these are all 100s in here. So that's 60 and 60 makes 120. 70, 70, 70, 70 makes 280. And then 7 times 6 makes 42. So these are all 70s in here. So that makes 42. And so now we add all this together. That's a 4. And so that's 1242. All right. So that gives us an answer there using this sort of more explicit and detailed rectangle. So now we can abstract this a little bit more and maybe not draw a rectangle that's so detailed. And so let's draw this rectangle out, but we're going to group this as 40 and 6 and then 20 and 7. So we're not going to look at all of the individual 10s and 1s sort of separately. We're going to group these things together. So 20 times 40 makes my 800. 7 times 4 makes 280. 20 times 6 makes 120. And then this is my 42. So you can see it's not really numerically any different. The only piece that's really different is that we're not thinking about this as two separate pieces, but we're just kind of taking this all as 120. And so all of this sum still works together the same way. This is 1080, this is 162, so 1242. The answer still comes out to be the same. Now, from this, we can start to look at maybe the distributive property and work through an intermediate algorithm that way, or we can start to build toward this algorithm, the standard algorithm. Let me fix this 7. All right. So if we look at this, I'm going to multiply this out in sort of this expanded form. So actually, let me change. So I'm going to multiply this out in expanded form. And so I can distribute the 6, or I can distribute the 7 rather to the 6 and get 42. the 7 to the 40, and that gives me the 280. Now I'm going to do the 20 to the 6, and that's 120. And then the 20 times the 40 makes 800. And so you should notice that these four numbers are the same as the four numbers inside this rectangle, and that really I've just applied the distributive property twice. I've distributed the 7 and the 20. And one of the good things about doing multiplication like this in this sort of expanded form is that these zeros are not magical. We don't just, we don't count places and put zeros and have no idea why zeros are going there. I mean, we're multiplying multiples of 10, and those multiples of 10 are creating those zeros. Now, from this, we'll go to the standard algorithm, 46 and 27. And so you can see where we're going from here. The 7 times 6 is my 42. And so there's my 4 from the 42 that's carrying over into the tens place. And so when I do the 7 times 4 and get 28 plus 4 makes 32. So this is this sum here. That's my 322 is the 7 times 6 and the 7 times 40. That's my 7 times 46. And the same thing's going to happen here. This 2 is really a 20 times 6 is 120. And so that's 120. So I'm going to carry the 1 over. And then the 2 times 4 plus the 1, 12, 42. So I get the same answer. And if I go back, I could look at this rectangle, and instead of adding vertically, I could add horizontally. And there's my 920, and there's my 322 there also. So I can connect it back this way. If I were to do this the other way and go 27 over 46, then I would see these numbers here along the bottom. It's interesting to me, for as many times as I've taught this sort of thing, that people are very proprietary about multiplying up or multiplying down, quote unquote. Either way works. I mean, there's commutativity, but you sort of bought into this process and it becomes sort of so ingrained in the way that you do these problems that you have that one approach that you want to work, and that's fine. It'd be good to show students multiple ways of sort of approaching this algorithm, but build proficiency with one before we start to move to the other. But again, you can see the same evolution from this concrete model to this slightly more abstracted model. It's still a concrete model, but it's maybe not as detailed. To here, this expanded form model, which is really expanded form and distributive property, but we're doing it vertically, so we're moving toward this algorithm until finally we get to here, the full standard algorithm. So the concrete model supports the algorithm calls back on the concrete model. They're working together to build this level of understanding. Once students see this mechanism and they start to see this evolution, we can apply this now to 3-digit, 4-digit, 5-digit numbers. We don't need to worry so much about the base 10 blocks really looking like base 10 blocks. And so if I wanted to use thousands or even 10,000s pieces, I certainly could. And I don't need to worry about the three-dimensionality being projected into 2 dimensions or anything wonky like that. If I wanted to do 158 times 3, I could just do 100 times 50 times 8. This is 300, this is 150, and this is 24. So I can just apply this distributive property and get 300. This is 450 and 24, 474. So there's my answer. And I can develop this into 3 times 158. Well, 8 times 3 is 24. This is 50 times 3 is 150. And this is 100 times 3 makes 300. So get the same thing. So once students see the connection between the two, it's easier to do each subsequent abstraction. The first one's going to take some time. It is an investment. It's an investment in not only your teaching time and your teaching effort, but in their understanding and their ability to abstract around this topic and generally around mathematics. So you'll put a lot of time into the first one, but the second one will go a lot smoother and a lot quicker and a lot easier. The third one will be even quicker. The fourth one, and then by the time you have enough done, students start to see the pattern, start to develop the pattern. They'll start asking you, "Oh, well, don't we just do this and then this and then this?" And then you know that they're at that level of proficiency and fluency. That's kind of where you want them to be. So this becomes abstractable to as many digits as we want. So for your checkpoint problem, there's nothing really too complex to this. I just want you to try to do this 3 by 2 digit multiplication problem. I will give you a little bit of a hint if you want it. So if you don't want it, stop the video now. But think about drawing a rectangle like this, a 3 by 2 rectangle, since we're dealing with a 3 digit by 2 digit number. And so think about doing this problem using this model, using a rectangular area model, and then solve it using the standard algorithm, and make sure you see the connection between the model and the algorithm. I mean, obviously your answers should be the same, because which way you solve the problem shouldn't change your solution. But make sure that you see that connection so you could explain and illustrate that connection to your students. So if you have any questions about this problem or anything else from this section, make sure you bring them to class and let me know. All right, thanks.